Good morning everyone, I am Thibault Lutelier and I'm going to present our work, CoCoNuT, combining context-aware neural translation models using Ensemble for program repair. This work was done in collaboration with Hung Pham, Lawrence Peng, Yitong Li, and Moshi Wei from University of Waterloo, as well as our supervisor, Professor Lin Tan from Purdue University. Manually fixing bugs is expensive, and developers spend most of their time fixing them. As of July 1st, 2020, there were more than 17,000 opened issues in Chromium that had no developer assigned to them. Therefore, automation will help fixing more bugs. Traditional automatic program repair often use a generate and validate approach. Given a buggy code location, existing generate and validate techniques build a search space using mutations or manually defined templates, then rank and select patches using some heuristics. Finally, each patch is validating against the test suite. If a patch passes all the test cases, it is considered a plausible patch and the process stops. Otherwise, the patch is discarded and we move to the next patch. This approach has two main issues. First, a previous study found that the search space often does not contain the correct patch. In addition, hard-coded templates need to be adapted to work with different programming languages, which require significant manual effort. To address these issues, neural machine translation is a natural approach to try. It is a deep learning approach commonly used in natural language. For example, given a sentence in French, the neural machine translation model will translate it into a semantically equivalent sentence in English. Our idea is that instead of translating French to English, we translate a buggy piece of code to a correct piece of code. Compared to traditional approaches, neural machine translation has the following two advantages. First, the fixed patterns are automatically discovered from a large training set. Therefore, the model can fix bugs existing approach cannot, despite years of research on manually defined patterns. Second, the neural machine translation architecture is not language dependent, so it can be adapted to different programming languages without much effort. Therefore, we propose CoCoNuT, a technique that uses a new context-aware neural machine translation architecture. We then use an ensemble approach to combine such architectures to automatically generate fixes for different bugs. CoCoNuT is the first approach to fix bugs in 4 different programming languages, including 309 bugs that had not been fixed automatically before. Here is an example of a bug that only CoCoNuT can fix in the popular Defects4J benchmark. This bug is a real bug from the Mockito project. The line starting with minus is a buggy line, while the line starting with a plus is a correct fix generated by CoCoNuT. This bug cannot be fixed by previous work because researchers and practitioners did not manually find the pattern update error type. CoCoNuT, on the other hand, can fix this bug because it infers this new pattern from millions of training samples mined from open source projects. This is another bug only CoCoNuT can fix. In this case, notice that the buggy location with a red background does not contain enough information to generate the correct fix with a blue background, because the variable type parameter and actual type argument are not in the buggy line. CoCoNuT can use a new context-aware deep learning architecture that represents the context of the bug and can therefore automatically generate a complete patch by extracting meaningful information from the context of the bug, such as correct variable names. While neural machine translation presents several advantages, there are also many challenges applying it to automatically fix bugs. In this talk, I'm going to talk about 4 of them. First, we will see how we select and represent the context of a bug. Second, we will explain how CoCoNuT can capture the diversity of bug fixes. Third, we will talk about a common mistake in the evaluation setup when evaluating machine learning approaches. Finally, we'll discuss the choice of neural machine translation architecture. These are 2 examples of bugs that have the same buggy line, return null. The correct fix, however, is different, and it is therefore difficult for the model to generate the correct fix without more information about the project. In practice, such information can be found in the surrounding line of the buggy location. For example, in the first case, the correct variables to introduce is in the body of the function. In the second case, we can get some clues about the correct return values from the function signature. Therefore, we decided to use the entire function surrounding the buggy line as context for our technique. Now the main question is, how do we represent such context to a neural machine translation architecture? So in natural language, neural machine translation takes a sentence as input, feed it to an encoder, and then a decoder generates an equivalent sentence in another language. As we just showed, applying this principle directly to program repair does not work well because the buggy line does not contain enough information to generate the fixed line. Naively, we can feed both the buggy line and its context to the encoder. However, in practice, this does not work well because a larger context overwhelms the buggy line. We address this problem by proposing a new architecture that uses 2 separate encoders for the buggy line and the context lines. The buggy line encoder learns relationship between the buggy line and the fixed line, while the context encoder learns relationship between the context and the fixed line. The merger layer ensures that both buggy and context encodings are treated equally, even if the buggy line is much smaller than the context. The second challenge is to capture the diversity of bug fixes. There are many different types of bugs, and they have many different fix patterns. For example, a buffer overflow bug will look very different from an error handling bug. It is difficult for one unique model to learn all these different fix patterns. Our solution is to train multiple models with different complexity and combine them using ensemble learning. Models with different complexity will capture different features and fix different bugs. Then, we use Ensemble to combine these models into a technique that can fix all of these bugs. The third challenge I want to talk about is the danger of incorrect setup. So there is a common mistake in the evaluation setup researchers need to be aware when evaluating machine learning approaches. This has been described with further detail for defect prediction in previous work, but we are the first to raise awareness of this issue for automatic program repair. So the models used in CoCoNuT are trained using data extracted from commits from open source projects. Commits are pushed by developers over time. For example, instance 4 here was fixed in 2005, while instance 8 was fixed in 2008. If we use it on the test benchmark, for example defect4j, and more specifically from the oldest bug in defect4j, which is from 2006, we have an incorrect and potentially biased setup. Indeed, the training instances in orange occurred after the bug under test was fixed. Such instances were not available at the time of the fix, and might provide our model information on how to fix a bug that will not be available in practice in a realistic setup. Using such instance to evaluate our model, using such instance in the training set to evaluate our model is incorrect, and might lead to artificially high results as described in previous work. The solution is to remove such instance from the training set. Finally, the last challenge concerns the choice of deep learning architecture. Recurrent neural networks, such as LSTM, are very common in natural language because they represent the input as a sequence and read it linearly, which is somehow similar to the way people read an English sentence. However, source code is generally not read linearly. Instead, developers often read source code by jumping from one location to another and looking at a different level of granularity, maybe focusing first on one variable, then looking at the bigger picture by looking at the entire code block. And we found that this is better represented by stacking convolutional layers of different kernel sizes. And I'm going to provide an example right now. So this is an overview of our model architecture. We have the input on the left, followed by the encoder that starts with an embedding layer. And then on the right, I'm showing the decoder, attention, and token generation that we won't describe much here. Here I'm going to focus on the encoder to explain at a high level why CNN layers are better than RNNs in our context. So in this example, the first convolutional layer has a small kernel size that will encode relations between closely related tokens. So for example, start and calendar. This represents information at a very low level. Then we continue with more layers of different kernel size, and eventually here we arrive to the third layer that has a larger kernel size than the first layers and will therefore encode relations between more distant tokens, and in this case can cover the tokens start, calendar, see, equal, and new. Finally, in this example, we reach the fourth convolutional layer that has an even larger kernel size, and that will be used to encode more distant relations and can cover, in this case, the relation between the function name, Gregorian calendar, and its parameter, m time zone. Therefore, the use of CNN here can encode relation at different level of granularity much more easily than recurrent neural network will do. I will now present the overview of our approach. First, in the training stage, we extract data from commits from open source projects in the following format. We have a buggy line in red, a fixed line in blue, and context line with purple block on the left. Then we tokenize these lines and tune many different models with different complexity for one epoch. Then we select the top K models that will be further trained until convergence. The inference stage represents how a user will use CoCoNuT. Given a buggy line on its context, CoCoNuT will tokenize it and feed it to the top K models. The output of these models will then be combined and ranked. Then the candidate patches will be validated against the test suite. The patches that pass all the test suite are considered plausible patches. We evaluate CoCoNuT on 6 benchmarks in 4 different programming languages, including Defect4j, the most popular benchmark. For evaluation, we consider a patch as correctly fixed not only if it passes all the test cases, but also if it is semantically equivalent to the developer patches. The reason is to filter out overfitted patches that will passes all the test cases but not be equivalent to developer patches. CoCoNuT can fix 509 bugs in this benchmark, including 309 bugs that have not been fixed by existing tools. CoCoNuT, and this is the first technique to fix bugs in 4 different programming languages. And this is the best technique in 4 of our 6 benchmarks. While it is only the third technique on Defect4j, it is outperformed by T-bar and Hercules. It can still fix 6 new bugs that none of the 22 other tools tested on Defect4j can fix, despite years of research and fixed templates. So to understand the impact of each element of CoCoNuT, we perform an ablation study on the defects4j benchmark. First, we measure the impact of the deep learning architecture, and we found that the context-aware architecture using CNN can outperform traditional architecture such as transformer and LSTM. Second, we measure the impact of context and found that our model that use context can fix 6 more bugs in the defect4j benchmark than the same model using no context. Finally, we found that using an ensemble of 10 models can double the number of bugs fixed by a single model, from 22 bugs fixed with one model to 44 bugs fixed using 10 different models. So that shows that the different parts of the defect4j of CoCoNuT all contribute to improving the results on the defect4j benchmark. So in conclusion, in this talk, I presented CoCoNuT, a new automatic program repair technique that uses Ensemble to combine new CNN context-aware neural machine translation architecture. CoCoNuT is able to fix 509 bugs in 4 different programming languages, including 309 that had not been fixed by previous techniques, despite years of research on manually fixed templates. I will now take questions. Thank you very much for your time.